attached to them, including our own bodies, and reversing that I'm not this little thing, a little consciousness trapped in the body. And the consciousness itself is only a product of the body. So when the body dies, the consciousness disappears. It turns completely around. The consciousness is fundamental. The body, my hand exists right now because I'm looking at it. My hand is gone. I have no hand. I have no brain. I have no heart. If you looked, you'll see a heart. Whatever I am is this really complicated thing in consciousness. That's what I am. All the stuff that I thought I was is something that I create on the fly and delete. So this is completely a radical restructuring of how we think about possessions, about identity, about survival of death, and so forth. This is completely transformative. But the nice thing is that this whole approach of conscious agents, unlike the spiritual traditions, which have said, in some cases, similar things, they've said it imprecisely. This is mathematics. We can actually now begin to state precisely, here's the mathematical model of consciousness, conscious agents, here's how it maps onto space-time, which I should sketch really briefly. And here's why things are ephemeral, and here's why you shouldn't be worried about the ephemeral nature of things, because you're not a little tiny entity inside space and time. Quite the opposite. You're the author of space and time.
The I and the am and the I am is all kind of emergent through this whole process of evolution and so on. That's just surface waves, and there's a much deeper ocean that we're trying to figure out here. So how does, you said some of the stuff you're thinking about maps to space-time. How does it map to space-time?
Right. So just a very, very high level, and I'll keep it brief. The structures that the physicists are finding, like the amplitude-hedron, it turns out they're just static structure. They're polytopes. But they, remarkably, most of the information in them is contained in permutation matrices. So it's a matrix, like an n by n matrix, that just has zeros and ones.
No zeros.
That contains almost all of the information. And you can, they have these Plavic graphs and so forth that they use to boot up the scattering. You can compute the scattering amplitudes almost entirely from these permutation matrices. So that's these loops.
Oops, I lost where it was now.
It's just interesting looking at the philosophical tradition of the difficult ideas you struggle with. If you look like somebody like Immanuel Kant, what are some interesting agreements and disagreements you have?
Well, your experience in front of you. To be aware of your experience in front of you. What you experience is just like a modeled dark gray. But there's some dynamics to it, but it's just dark gray.
So I'm gonna do the series to this guy, Donald Hoffman, but I guess so. Trying to decide if I'm gonna start this all over or so I gotta record it.
We don't have to just wave our hands. Evolution of a natural selection is a mathematically precise theory. John Maynard Smith in the 70s created evolutionary game theory. And We have evolutionary graph theory and even genetic algorithms that we can use to study this. And so we don't have to wave our hands. It's a matter of theorem and proof and or simulation before you get the theorems and proofs. And a couple of graduate students of mine, Chester Mark and Brian Marion, did some wonderful simulations that tipped me off that there was something going on here. And then I went to a mathematician, Clayton Prakash and Manish Singh, and some other friends of mine, Chris Fields. But Clayton was the real mathematician behind all this, and he's proved several theorems that uniformly indicate that, with one exception, which has to do with probability measures, there's no, the probability is zero. The reason there's an exception for probability measures, so-called sigma algebras or sigma additive classes, is that for any scientific theory, there is the assumption that needs to be made that whatever structure, whatever probabilistic structure the world may have, is not unrelated to the probabilistic structure of our perceptions. If they were completely unrelated, then no science would be possible. So this is technically the map from reality to our senses has to be a so-called measurable map. It has to preserve sigma algebras. But that means it could be infinite to one, and it could collapse all sorts of event information. But other than that, there's no requirement in standard evolutionary theory for fitness payoff functions, for example, to preserve any specific structures of objective reality. So you can ask the technical question. This is one of the avenues we took. If you look at all the fitness payoffs from whatever world structure you might want to imagine. So a world with, say, a total order on it. So it's got n states, and they're totally ordered. And then you can have a set of maps from that world into a set of payoffs, say from 0 to 1,000 or whatever you want your payoffs to be. And you can just literally count all the payoff functions and just do the combinatorics and count them. And then you can ask a precise question. How many of those payoff functions preserve the total order, if that's what you're looking, or how many preserve the topology? And you just count them and divide. So the number that are homomorphisms versus the total number, and then take the limit as the number of states in the world, and the number of payoff values goes very large. And when you do that, you get 0 every time.
Okay, there's a million things to ask here, but first of all, just in case people are not familiar with your work, let's sort of linger on the big, bold statement here, which is the thing we see with our eyes is not some kind of limited window into reality that is completely detached from reality, likely completely detached from reality. You're saying 100% likely. Okay, so none of this is real in the way we think is real, in the way we have this intuition. There's like this table is some kind of abstraction, but underneath it all, there's atoms. And there's an entire century of physics that describes the functioning of those atoms and the quarks that make them up. There's many Nobel Prizes about particles and fields and all that kind of stuff that slowly builds up to something that's perceivable to us, both with our eyes, with our different senses, as this table. Then there's also ideas of chemistry that over layers of abstraction, from DNA to embryos to cells, that make the human body. So all of that is not real.
It's a real experience, and it's a real adaptive set of perceptions. So it's an adaptive set of perceptions, full stop. We want to think that
Perceptions are real.
So their perceptions are real as perceptions. Right? They are. We are having our perceptions, but we've assumed that there's a pretty tight relationship between our perceptions and reality. If I look up and see the moon, then there is something that exists in space and time that matches what I perceive. And all I'm saying is that if you take evolution by natural selection seriously, then that is precluded.
Don't.
That our perceptions are there. They're there to guide adaptive behavior, full stop. They're not there to show you the truth. In fact, the way I think about it is they're there to hide the truth because the truth is too complicated. It's just like if you're trying to use your laptop to write an email. right? What you're doing is toggling voltages in the computer. But good luck trying to do it that way. The reason why we have a user interface is because we don't want to know that quote-unquote truth, the diodes and resistors and all that terrible hardware. If you had to know all that truth, it would, your friends wouldn't hear from you. So what evolution gave us was perceptions that guide adaptive behavior, and part of that process, it turns out, means hiding the truth and giving you eye candy.
So, what's the difference between hiding the truth and forming abstractions, layers upon layers of abstractions over low-level voltages and transistors and chips and programming languages from assembly to Python that then leads you to be able to have an interface like Chrome where you open up another set of JavaScript and HTML programming languages that lead you to have a graphical user interface on which you can then send your friends an email. Is that completely detached from the zeros and ones that are firing away inside the computer?
It's not. Of course, when I talk about the user interface on your desktop, there's this whole sophisticated backstory to it, right? That the hardware and the software that's allowing that to happen. Evolution doesn't tell us the backstory, right? So the theory of evolution is not going to be adequate to tell you what is that backstory. It's going to say that whatever reality is, and that's the interesting thing, it says whatever reality is, you don't see it. You see a user interface, but it doesn't tell you what that user interface is, how it's built.
People like you make it hard for anybody to go see it.
We can try to look at certain aspects of the interface, but already we're going to look at that and go, okay, before I would look at neurons and I was assuming that I was seeing something that was at least partially true. And now I'm realizing it could be like looking at the pixels on my desktop or icons on my desktop, and good luck, going from that to the data structures and then the voltages, and good luck. There's just no way. So what's interesting about this is that our scientific theories are precise enough and rigorous enough to tell us certain limits, and even limits of the theories themselves. But they're not going to tell us what the next move is, and that's where scientific creativity comes in. So the stuff that I'm saying here, for example, is not alien to physicists. The physicists are saying precisely the same thing, that space-time is doomed. We've assumed that space-time is fundamental. We've assumed that for several centuries, and it's been very useful. So all the things that you were mentioning, the particles and all the work that's been done, that's all been done in space-time. But now physicists are saying space-time is doomed. There's no such thing as space-time fundamentally in the laws of physics. And that comes actually out of gravity together with quantum field theory. It just comes right out of it. It's a theorem of those two theories put together. But it doesn't tell you what's behind it. So the physicists know that their best theories, Einstein's gravity and quantum field theory put together, entail that space-time cannot be fundamental, and therefore particles in space-time cannot be fundamental. They're just irreducible representations of the symmetries of space-time. That's what they are. So space-time, so we put the two together. We put together what the physicists are discovering, and we can talk about how they do that. And then the new discoveries from evolution and natural selection. Both of these discoveries are really in the last 20 years. And what both are saying is space-time has had a good ride. It's been very useful. Reductionism has been useful, but it's over. And it's time for us to go beyond.
When you say space-time is doomed, is it the space? Is it the time? Is it the very hard-coded specification of 4 dimensions? Or are you specifically referring to the kind of perceptual domain that humans operate in, which is space-time? You think like there's a 3D, like our world is 3-dimensional and time progresses forward, therefore 3 dimensions plus 1, 4D. What exactly do you mean by space-time? What do you mean by space-time is doomed?
Great. So this is, by the way, not my quote. This is from, for example, Nima Arkani-Hamed at the Institute for Advanced Study at Princeton, Ed Witten, also there, David Gross, Nobel Prize winner. So this is not just something the cognitive scientists, this is what the physicists are saying.
Yeah, the physicists are space-time skeptics.
Well, yeah, they're saying that, and I can say exactly why they think it's doomed, but what they're saying is that, because your question was, what aspect of space-time, what are we talking about here? It's both space and time, their union into space-time, as in Einstein's theory. That's doomed. And they're basically saying that even quantum theory, this is Nima Arkani Hamed especially, so Hilbert spaces will not be fundamental either. So that the notion of Hilbert space, which is really critical to quantum field theory, quantum information theory, that's not going to figure in the fundamental new laws of physics. So what they're looking for is some new mathematical structures beyond space-time, beyond Einstein's four-dimensional space-time or supersymmetric version, geometric algebra signature 2,4 kind of. There are different ways that you can represent it, but they're finding new structures, and by the way, they're succeeding now. They found something called the amplituhedron. This is Nima and his colleagues, the cosmological polytope. There are these like polytopes, these polyhedra in multi-dimensions, generalizations of simplices, that are coding for example, the scattering amplitudes of processes in the Large Hadron Collider and other colliders. So they're finding that if they let go of space-time completely, they're finding new ways of computing these scattering amplitudes that turn literally billions of terms into one term. When you do it in space and time, because it's the wrong framework, it's just a user interface. That's now from the evolutionary point of view. It's just user interface. It's not a deep insight into the nature of reality. So it's missing deep symmetry. It's something called a dual conformal symmetry, which turns out to be true of the scattering data, but you can't see it in space-time. And it's making the computations way too complicated because you're trying to compute all the loops and Feynman diagrams and all the Feynman integrals. So see, the Feynman approach to the scattering amplitudes is trying to enforce two critical properties of space-time: locality and unitarity. And so when you enforce those, you get all these loops and multiple, different levels of loops, and for each of those you have to add new terms to your computation. But when you do it outside of space-time, you don't have the notion of unitarity. You don't have the notion of locality. You have something deeper, and it's capturing some symmetries that are actually true of the data. But then when you look at the geometry of the facets of these polytopes, then certain of them will code for unitarity and locality. So it actually comes out of the structure of these deep polytopes. So what we're finding is there's this whole new world now beyond space-time that is making explicit symmetries that are true of the data that cannot be seen in space-time, and that is turning the computations from billions of terms to one or two or a handful of terms. So we're getting insights into symmetries, and all of a sudden the math is becoming simple because we're not doing something silly. We're not adding up all these loops in space-time. We're doing something far deeper. But they don't know what this world is about. So, they're in an interesting position where we know that space-time is doomed, and I should probably tell you why it's doomed, what they're saying about why it's doomed. But they need a flashlight to look beyond space-time. What flashlight are we going to use to look into the dark beyond space-time? Because Einstein's theory and quantum theory can't tell us what's beyond them. All they can do is tell us that when you put us together, space-time is doomed at 10 to the minus 33 centimeters, 10 to the minus 43 seconds. Beyond that, space-time doesn't even make sense. It just has no operational definition. So, but it doesn't tell you what's beyond. And so they're just looking for deep structures, like guessing. It's really fun. So these really brilliant guys, generic, brilliant men and women who are doing this work, physicists, are making guesses about these structures. Informed guesses, because they're trying to ask, okay, what deeper structure could give us the stuff that we're seeing in space-time, but without certain commitments that we have to make
it distracts
in space-time,
everyone,
like locality.
so
So they make these brilliant
they can't
guesses,
go
and of
see
course
it for
most of the time they'll be
themselves.
wrong. But once you get one or two that start to pay off, and then you get some lucky breaks. So they got a lucky break back in 1986. A couple of mathematicians named Park and Taylor took the scattering amplitude for 2 gluons coming in at high energy and 4 gluons going out at low energy. So that kind of scattering thing. So it's like apparently for people who are into this, that's sort of something that happens so often you need to be able to find it and get rid of those because you already know about that and you need to. So you needed to compute them. It was billions of terms. And they couldn't do it, even for the supercomputers couldn't do that for the many billions or millions of times per second they needed to do it. So they begged, the experimentalists begged the theorists, please, you got it. And so Park and Taylor took the billions of terms, hundreds of pages, and miraculously turned it into 9. And then a little bit later, they guessed one term expression that turned out to be equivalent. So billions of terms reduced to one term, the so-called famous Park-Taylor formula, 1986. And that was like, okay, where did that come from? What? This is a pointer into a deep
Look at
realm
that shit, huh?
beyond space and time.
It's
but
unfucking
no
real,
one,
man.
I mean, what can you do with it? And they thought maybe it was a one-off, but then other
Fucking
formulas
real.
started coming up. And then eventually Nima Arkani Hamed and his team found this thing called the amplitude-hedron, which really sort of captures the whole, a big part of the whole dynamics. But I'm sure they would say, no, there's plenty more to do. So I won't say they did it all by any means. They're looking at the cosmological polytope as well. So what's remarkable to me is that two pillars of modern science, quantum field theory with gravity on the one hand, and evolution by natural selection on the other, just in the last 20 years have very clearly said space-time has had a good run. Reductionism has been a fantastic methodology. So we had a great ontology of space-time, a great methodology of reductionism. Now it's time for a new trick. But now you need to go deeper and show, but by the way, this doesn't mean we throw away everything we've done, not by a long shot. Every new idea that we come up with beyond space-time must project precisely into space-time, and it better give us back everything that we know and love in space-time, or generalizations. Or it's not going to be taken seriously, and it shouldn't be. So we have a strong constraint on whatever we're going to do beyond space-time. It needs to project into space-time, and whatever this deeper theory is, it may not itself have evolution by natural selection. This may not be part of this deeper realm. But when we take whatever that thing is beyond space-time and project it into space-time, it has to look like evolution by natural selection, or it's wrong. So that's a strong constraint on this work.
So even the evolution by natural selection and quantum field theory could be interfaces into something that doesn't look anything like you mentioned. I mean, it's interesting to think that evolution might be a very crappy interface into something much deeper.
That's right. They're both telling us that the framework that you've had can only go so far, and it has to stop. And there's something beyond. And that framework, the very framework that is space and time itself. Now, of course, evolution by natural selection is not telling us about, like Einstein's relativistic space-time. So that was another question you asked a little bit earlier. It's telling us more about our perceptual space and time, which we have used as the basis for creating first a Newtonian space versus time as a mathematical extension of our perceptions. And then Einstein then took that and extended it even further. So the relationship between what evolution is telling us and what the physicists are telling us is that, in some sense, the Newton and Einstein space-time are formulated as sort of rigorous extensions of our perceptual space, making it mathematically rigorous and laying out the symmetries that they find there. So that's sort of the relationship between them. So it's perceptual space-time that evolution is telling us is just a user interface, effectively. And then the physicists are finding that even the mathematical extension of that into the Einsteinian formulation has to be as well not the final story. There's something deeper.
So let me ask you about reductionism and interfaces as we march forward from Newtonian physics to quantum mechanics. These are all, in your view, interfaces. Are we getting closer to objective reality? How do we know if these interfaces in the process of science, the reason we like those interfaces is because they're predictive of some aspects, strongly predictive about some aspects of our reality. Is that completely deviating from our understanding of that reality, or is it helping us get closer and closer and closer?
Well, of course, one critical constraint on all of our theories is that they are empirically tested and pass the experiments that we have for them. So no one's arguing against experiments being important and wanting to test all of our current theories and and any new theories on that. So that's all there. But we have good reason to believe that science will never get a theory of everything.
Everything.
Everything, right, a final theory of everything, right. I think that my own take is, for what it's worth, is that Gödel's incompleteness theorem sort of points us in that direction, that even with mathematics, any finite axiomatization that's sophisticated enough to be able to do arithmetic, it's easy to show that there'll be statements that are true, that can't be proven, can't be deduced from within that framework. And if you add the new statements to your axioms, then there'll be always new statements that are true but can't be proven with the new axiom system. And the best scientific theories, in physics, for example, and also now evolution, are mathematical. So our theories are going to be, they're going to have their own assumptions, and they'll be mathematically precise. And there'll be theories perhaps of everything except those assumptions, because the assumptions are, when we say, please grant me these assumptions, if you grant me these assumptions, then I can explain this other stuff. But so you have the assumptions that are like miracles as far as the theory is concerned. They're not explained. They're the starting points for explanation. And then you have the mathematical structure of the theory itself, which will have the Gödel limits. And so my take is that reality, whatever it is always going to transcend any conceptual theory that we can come up with.
There's always going to be mystery at the edges.
Right.
Contradictions and all that kind of stuff. Okay.
And truths.
So there's this idea that is brought up in the financial space of settlement of transactions. It's often talked about in cryptocurrency especially. So you could do, money, cash is not connected to anything. It used to be connected to gold, to physical reality, but then you can use money to exchange value, transact. So when it was in the gold standard, the money would represent some stable component of reality. Isn't it more effective to avoid things like hyperinflation, if we generalize that idea? Isn't it better to connect your whatever we humans are doing in the social interaction space with each other? Isn't it better from an evolutionary perspective to connect it to some degree to reality, so that the transactions are settled with something that's universal, as opposed to us constantly operating in something that's a complete illusion? Isn't it easy to hyperinflate that? Like where you really deviate very, very far away from the underlying reality? Or do you never get in trouble for this? Can you just completely drift far, far away from the underlying reality and never get in trouble?
That's a great question. So, on the financial side, there's two levels at least that we could take your question. One is strictly like evolutionary psychology of financial systems, and that's pretty interesting. And there, the decentralized idea, the DeFi kind of idea in cryptocurrencies, may make good sense from just an evolutionary psychology point of view. Having human nature being what it is, putting a lot of faith in a few central controllers depends a lot on the veracity of those and trustworthiness of those few central controllers. And we have ample evidence, time and again, that that's often betrayed. So it makes good evolutionary sense, I would say, to have a decentralized. I mean, democracy is a step in that direction, right? We don't have a monarch now telling us what to do. We decentralize things, right? Because if you have Marcus Aurelius as your emperor, you're great. If you have Nero, it's not so great. And so we don't want that. So democracy is a step in that direction, but I think the DeFi thing is an even bigger step, and is going to even make the democratization even greater. So that's one level of.
Also, the fact that power corrupts and absolute power corrupts absolutely is also a consequence of evolution.
Right.
That's also a feature, I think. Right? You can argue from the long span of living organisms, it's nice for power to corrupt, for you to, madmen and women throughout history might be useful to teach us a lesson.
We can learn from
About
our
ourselves.
negative example, right?
Exactly.
Right. Right. So power does corrupt, and I think that you can think about that again from an evolutionary point of view. But I think that your question was a little deeper when that was, does the evolutionary interface idea sort of unhinge science from some kind of important test for the theories, right? We don't want, doesn't mean that anything goes in scientific theory, but there's no, if we don't see the truth, is there no way to tether our theories and test them? And I think there's no problem there. We can only test things in terms of what we can measure with our senses in space and time. So we're going to have to continue to do experiments, but we're going to understand a little bit differently what those experiments are. We had thought that when we see a pointer on some machine in an experiment, that the machine exists, the pointer exists, and the values exist even when no one is looking at them, and that they're an objective truth. And our best theories are telling us no. The pointers are just pointers, and that's what you have to rely on for making your judgments. But that even the pointers themselves are not the objective reality. So, and I think Gödel is telling us that, not that anything goes, but as you develop new axiom systems, you will find out what goes within that axiom system and what testable predictions you can make. So I don't think we're untethered. We continue to do experiments. What I think we won't have that we want is a conceptual understanding that gives us a theory of everything that's final and complete. I think that this is, to put it another way, this is job security for scientists. Our job will never be done. It's job security for neuroscience. Because before we thought that when we looked in the brain, we saw neurons and neural networks and action potentials and synapses and so forth, and that was it. That was the reality. Now we have to reverse engineer that. We have to say, what is beyond space-time? What is going on? What is a dynamical system beyond space-time that when we project it into Einstein's space-time gives us things that look like neurons and neural networks and synapses? So we have to reverse engineer it. So there's going to be lots more work for neuroscience. It's going to be far more complicated and difficult and challenging. But that's wonderful. That's what we need to do. We thought neurons exist when they are perceived, and they don't. In the same way that if I show you, when I say they don't exist, I should be very, very concrete. If I draw on a piece of paper a little sketch of something that is called the Necker cube, it's just a little line drawing of the cube, but it's on a flat piece of paper. If I execute it well, and I show it to you, you'll see a 3D cube, and you'll see it flip. Sometimes you'll see one face in front, sometimes you'll see the other face in front. But if I ask you, which face is in front?
Yeah,
you
you
don't
gotta
look.
keep running in, huh?
The answer is, well, neither face is in front because there's no cube. There's just a flat piece of paper.
Yeah.
So when you look at the piece of paper, you perceptually create the cube. And when you look at it, then you fix one face to be in front and one face to be in. So that's what I mean when I say it doesn't exist. Space-time itself is like the cube. It's a data structure that your sensory systems construct, whatever your sensory systems mean now, because
Sure.
we now have to not even take that for granted. But there are perceptions that you construct on the fly.
Oh my God.
And they're data structures in a computer science, and you garbage collect them when you don't need them. So you create them and garbage collect them.
But is it possible that it's mapped well in some concrete, predictable way to objective reality? The sheet of paper, this two-dimensional space, or we can talk about space-time, maps in some way that we maybe don't yet understand, but will one day understand what that mapping is. But it maps reliably. It is tethered in that way.
Well, yes, and so the new theories that the physicists are finding beyond space-time have that kind of tethering. So they show precisely how you start with an amplitude-hedron and how you project this high-dimensional structure into the 4 dimensions of space-time. So there's a precise procedure that relates the two, and they're doing the same thing with the cosmological polytopes. So they're the ones that are making the most concrete and fun advances going beyond space-time, and they're tethering it. Right, they say that this is precisely the mathematical projection from this deeper structure into space-time. Now, one thing I'll say about, as a non-physicist, that I find interesting is that they're finding just geometry, but there's no notion of dynamics. Right now, they're just finding these static geometric structures, which is impressive. So I'm not putting them down. This is what they're doing is unbelievably complicated and brilliant and adventurous. And it's all those things.
And beautiful,
and beautiful, yeah, right.
From a human aesthetic perspective, because geometry is beautiful.
It's absolutely, and they're finding symmetries that are true of the data that can't be seen in space-time. But I'm looking for a theory beyond space-time that's a dynamical theory. I would love to find, and we can talk about that at some point, a theory of consciousness in which the dynamics of consciousness itself will give rise to the geometry that the physicists are finding beyond space-time. If we can do that, then we'd have a completely different way of looking at how consciousness is related to what we call the brain or the physical world more generally. Right now, all of my brilliant colleagues, 99% of them, are trying to, they're assuming space-time is fundamental. They're assuming that particles are fundamental, quarks, gluons, leptons, and so forth. Elements, atoms, and so forth are fundamental, and that therefore neurons and brains are part of objective reality. And that somehow when you get matter that's complicated enough, it will somehow generate conscious experiences by its functional properties. Or if you're panpsychist, maybe you, in addition to the physical properties of particles, you add a consciousness property as well. And then you combine these physical and conscious properties to get more complicated ones. But they're all doing it within space-time. All of the work that's being done on consciousness and its relationship to the brain is all assumed something that our best theories are telling us is doomed, space-time.
Why does that particular assumption bother you the most? So you bring up space-time. I mean, that's just one useful interface we've used for a long time. Surely there's other interfaces. Is space-time just one of the big ones that to build up people's intuition about the fact that they do assume a lot of things strongly? Or is it in fact a fundamental flaw in the way we see the world?
Well, everything else that we think we know are things in space-time.
Sure.
And so when you say space-time is doomed, this is a shot to the heart of the whole framework, the whole conceptual framework that we've had in science. Not to the scientific method, but to the fundamental ontology and also the fundamental methodology, the ontology of space-time and its contents, and the methodology of reductionism, which is that as we go to smaller scales in space-time, we will find more and more fundamental laws. And that's been very useful for space and time for centuries, reductionism for centuries, but now we realize that that's over. Reductionism is in fact dead, as is space-time.
What exactly is reductionism? What is the process of reductionism that is different than some of the physicists that you mentioned that are trying to let go of the assumption of space-time, looking beyond? Isn't that still trying to come up with a simple model that explains this whole thing? Isn't it still reducing?
It's a wonderful question because it really helps to clarify two different notions, which is scientific explanation on the one hand, and a particular kind of scientific explanation on the other, which is the reductionist. So the reductionist explanation is saying, I will start with things that are smaller in space-time and therefore more fundamental, where the laws are more fundamental. So we go to just smaller and smaller scales. Whereas in science more generally, we just say, like when Einstein did the special theory of relativity, he's saying, let me have a couple postulates. I will assume that the speed of light is universal for all observers in uniform motion, and that the laws of physics, so if you're for uniform motion, are that's not a reductionist. Those are saying, grant me these assumptions, I can build this entire concept of space-time out of it. It's not a reductionist thing. You're not going to smaller and smaller scales of space. You're coming up with these deep, deep principles. Same thing with this theory of gravity, right? It's the falling elevator idea, right? So this is not a reductionist kind of thing. It's something different.
So simplification is a bigger thing than just reductionism.
Reductionism has been a particularly useful kind of scientific explanation, for example, in thermodynamics, right? Where the notion that we have of heat, some macroscopic thing like temperature and heat. It turns out that, Boltzmann and others discovered, well, hey, if we go to smaller and smaller scales, we find these things called molecules or atoms. And if we think of them as bouncing around and having some kind of energy, then what we call heat is really can be reduced to that. And so that's a particularly useful kind of reduction, is a useful kind of scientific explanation that works within a range of scales within space-time. But we know now precisely where that has to stop, at 10 to the minus 33 centimeters and 10 to the minus 43 seconds. And I would be impressed if it was 10 to the minus 33 trillion centimeters. I'm not terribly impressed at 10 to the minus 33 centimeters.
I don't even know how to comprehend either of those numbers, frankly. Just a small aside, because I am a computer science person, I also find cellular automata beautiful.
Yes.
And so you have somebody like Stephen Wolfram, who recently has been very excitedly exploring a proposal for a data structure that could be the numbers that would make you a little bit happier in terms of scale, because they're very, 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 very tiny. So do you like this space of exploration, of really thinking, letting go of space-time, letting go of everything, and trying to think what kind of data structures could be underneath this whole mess?
That's right. So if they're thinking about these as outside of space-time, then that's what we have to do. That's what our best theories are telling us. You now have to think outside of space-time. Now, of course, I should back up and say, we know that Einstein surpassed Newton, right? But that doesn't mean that there's not good work to do on Newton. There's all sorts of Newtonian physics that takes us to the moon and so forth, and there's lots of good problems that we want to solve with Newtonian physics. The same thing will be true of space-time. We'll still, it's not like we're going to stop using space-time. We'll continue to do all sorts of good work there. But for those scientists who are really looking to go deeper, to actually find the next, just like what Einstein did to Newton, what are we going to do to Einstein? How do we get beyond Einstein and quantum theory to something deeper? Then we have to actually let go. And if we're going to do like this automata kind of approach, it's critical that it's not automata in space-time, it's automata prior to space-time, from which we're going to show how space-time emerges. If you're doing automata within space-time, well, that might be a fun model, but it's not the radical new step that we need.
Yeah, so the space-time emerges from that whatever system. Yeah, like you're saying, it's a dynamical system. Do we even have an understanding what dynamical means when we go beyond? When you start to think about dynamics, it could mean a lot of things. Even causality could mean a lot of things if we realize that everything's an interface. Right. How much do we really know is an interesting question, because you brought up neurons. I gotta ask you another tangent. There's a paper I remember a while ago looking at called Could a Neuroscientist Understand a Microprocessor? And I just enjoyed that thought experiment that they provided, which is it's a couple of neuroscientists, Eric Jonas and Conrad Cording, who use the tools of neuroscience to analyze a microprocessor, so a computer chip.
Now, if we lesion it here, what happens and so forth, and if you go and lesion in a computer, it's very, very clear that lesion experiments on computers are not going to give you a lot of insight into how it works.
And also the measurement devices and the kind of just using the basic approaches of neuroscience, collecting the data, trying to intuit about the underlying function of it. And that helps you understand that our scientific exploration of concepts, depending on the field, are maybe in the very, very early stages. I wouldn't say it leads us astray. Perhaps it does sometimes, but it's not anywhere close to some fundamental mechanism that actually makes a thing work. I don't know if you can sort of comment on that in terms of using neuroscience to understand the human mind and neurons. Are we really far away potentially from understanding in the way we understand the transistors enough to be able to build a computer. So one thing about understanding is you can understand for fun. The other one is to understand so you could build things, and that's when you really have to understand.
Exactly. In fact, what got me into the field that I at MIT was work by David Marr on this very topic. So David Marr was a professor at MIT, but he'd done his PhD in neuroscience, studying just the architectures of the brain. But he realized that his work, it was on the cerebellum. He realized that his work, as rigorous as it was, left him unsatisfied because he didn't know what the cerebellum was for.
Yeah.
And why it had that architecture. And so he went to MIT and he was in the AI lab there. And he said he had this 3-level approach that really grabbed my attention. So when I was an undergrad at UCLA, I read one of his papers in a class and said, who is this guy? Because he said you have to have a computational theory. What is being computed and why? An algorithm. How is it being computed? What are the precise algorithms? And then the hardware. How does it get instantiated in the hardware? So to really do neuroscience, he argued, we needed to have understanding at all those levels. And that really got me. I loved the neuroscience, but I realized this guy was saying if you can't build it, you don't understand it effectively. And so that's why I went to MIT. And I had the pleasure of working with David until he died just a year and a half later. So there's been that idea that, with neuroscience, we have to have, in some sense, a top-down model of what's being computed and why, that we would then go after. And the same thing with trying to reverse engineer, a computing system like your laptop. We really need to understand what the user interface is about and why what are keys on the keyboard for and so forth. You need to know why to really understand all the circuitry and what it's for. Now, evolution by natural selection does not tell us the deeper question that we're asking, the answer to the deeper question, which is why. What's this deeper reality? And